Watch this. We will be building a machine learning system that can input the videos of football games and identify the balls and the individual players in the field. We will also map visible players into a radar-like map as shown here that visualizes the live positions of everyone as they run around in the field. We will do this by implementing the YOLO algorithm from scratch, meaning we will make our own neural network and train it on a custom football detection dataset. If you don't know about YOLO or you only look once, it's a computer vision algorithm that utilizes neural networks to detect and localize interesting objects in the scene. This is a long project, so I decided to divide it into two videos. In this first video, we will understand what YOLO is and neural network architectures like the darknet and feature pyramid networks or FPN, and how to implement all of that in Python starting from a completely blank file. In the second video, which should come out in a week or two, we will talk about how to track individual players as they dynamically run around the field, classify which player is playing for which team, and most amazingly, how to map them in this flat, radar-like 2D field map. Keep in mind that you don't really need to implement your own YOLO model if you want to do object detection. You can just use one of the off-the-shelf models that already comes, and within just 4 to 5 lines of code, you can fine-tune it on pretty much any custom problem. But this is a deep learning channel, and here we don't deal in black boxes. We want to learn what is inside this black box. What does this YOLO model even do? And by the end of this video, you'll hopefully understand some of the major concepts of YOLO models and how to implement them on your own. First up, what is object detection? Simply put, it's a technique used in computer vision to identify and locate objects within an image or a video. You must have heard about image classification, which asks the model what is in an image. Object detection takes this problem one step further by asking the model to draw a bounding box around each detected object and label it. So it answers the question, where in the image are which objects? And one of the most popular object detection model is the YOLO model, or you only look once model. The name YOLO comes from the fact that this algorithm looks at an image exactly once and predicts all the bounding boxes for all the objects in just that one single forward pass. This makes YOLO run pretty fast, and therefore it is the go-to choice for many real-time object detection applications. It can literally detect everything everywhere all at once. The input to a YOLO model will be just a single image. The model divides the input image into a grid and predicts bounding boxes within each grid cell. Each bounding box is represented by a set of values like the center x and y coordinates of the box, the width, the height of the box, and probabilities of which class the detected objects belong to. We will discuss details about this shortly. But to train a YOLO model, we also need a dataset of annotated images. Luckily, there is a great Roboflow dataset for football detection, which we can use. Please do check out their channel in the link below for more details about how this dataset was obtained. Basically, this dataset contains around 300 annotated images, which we are going to use to train our YOLO model. For each image, the data also provides a set of annotated bounding boxes. Each bounding box contains 5 values: the class ID, center x, center y, width, and height. Before we can use this data to train our YOLO neural network, we must first convert these annotations into that grid-like format that we discussed earlier. For example, let's say we have an image of size 200 by 200, and for our prediction, we choose the target cell size to be 20 by 20. This means that our prediction space will be a 10 by 10 grid. Now, let's say one of our annotation was 0.36, 0.22, 0.05, and 0.1. Again, 0.36 and 0.22 just represent the center x and y, and 0.05 and 0.1 are the width and the height of the annotated object. This bounding box obviously falls in the 4th row and 3rd column of our grid. The center of this cell is 0.35, 0.25. Therefore, the relative center of our annotation bounding box with respect to this cell will be 0.01 and minus 0.03. Therefore, the normalized prediction bounding box for this cell will have a vector of size 9 containing an objectness score, which indicates if an object is even present in this cell. Then the center x, center y then the width and the height, which are also relative to the image's size, and finally the class of which the object belongs to. For example, if it's a player object and the player index is 1, we will have 0, 1, 0, 0 as the one-hot encoding that will also be a part of this prediction. We will repeat the same process for all bounding boxes in our annotation list, creating a grid of 10 by 10 by 9, where the 10 by 10 are the number of rows and columns in the prediction space, and 9 is of course the bounding box vector we want to predict. For empty cells, we will just fill everything with zeros. At this point, let's pause the video and answer this question. What do you think is a huge flaw with the current way we are encoding bounding boxes? Well, a problem crops up if we have multiple objects that are very close by and fall within the same grid cell. Since our prediction vector only captures a single bounding box per cell, it will be impossible to detect more than one object if they are super close to each other and are competing within the same grid. A more general approach, therefore, will be to create more than just one prediction for each cell, maybe multiple, like 3 separate detection maps, making the prediction go from 10 by 10 by 9 to 3 by 10 by 10 by 9. Now our model will be trained to predict up to 3 bounding boxes per grid cell. Now obviously if there are more than 3, it's still gonna fail, but 3 is a good starting number, and depending on your use case and how close different objects are within your scene, you may want to decrease the grid size itself or increase the number of detection layers. This is the Python function I used to code this. First, you initialize a 4D NumPy array of shape, detection maps, grid size, and 5 plus num classes. We iterate over each bounding box in the input annotation, which contains entries as the class ID, the center x and y, width, and the height of the bounding boxes. Then the code scales and normalizes the center coordinates to the grid space, calculating the grid cell indices and clamping them to the grid boundaries. We find an available detection layer, meaning the first layer which has not been occupied yet, and attach the normalized bounding box details onto it. And the final output is our 4D target tensor. Alrighty, so we have pre-processed the training labels to a format that our model will be able to predict in. The training images also need to be pre-processed. Specifically, I used data augmentation with the Albumentations library. Data augmentation lets us generate new images from existing ones in the training data by basically artificially inflating it. I used augmentation techniques like horizontal flipping, random cropping, minor rotations, and adjusting the brightness and hue. A really cool feature in the Albumentations library is that you can also input bounding boxes into the model, and it automatically applies the same transformation to your input bounding boxes. So if cropping an image resulted in an object getting cut out of the scene, the associated bounding box will also be removed. Pretty cool. For all experiments, I used an input image size of 512 by 512 and used 16 by 16 grid cells, which means that the final target dimensions is 3 by 32 by 32 by 9 for each image. Next, we will build our neural network pipeline to train our YOLO model. In general, there are 3 main sections of a YOLO model: the backbone, the neck, and the head. The backbone is the initial feature extractor that processes the input image, and the stem further transforms these features, and then the head finally converts them into the bounding boxes that we need to generate. We will start off with the simplest approach. Each of these modules will be just simple convolutional neural network architectures, and let's see where we can reach by this simple model. And later on, we will add more complexity by using feature pyramid networks or FPN, but more on that a bit later. Also, if you're unfamiliar with CNNs in general, we have covered CNNs a bunch of times on this channel, so make sure you find these 2 videos if you want a more in-depth analysis of how CNNs work. Also, if you're liking this video, please do hit the like button, please subscribe to the channel for more content around machine learning, and do check out our Patreon page. I do regularly upload all of the code, walkthroughs, slides, Word documents, everything that goes into these videos on that Patreon page, so please do make sure that you check it out. And also a huge thank you for all of our channel members and patrons, because you make this channel run so smoothly and you inspired me, and you guys are magnificent. Let's get back to the video. For the backbone, I just initially stacked 3 convolution layers one after the other. In the YOLO context, this is often called as the darknet architecture, a series of fully convolutional layers that use residual connections, batch normalization, and leaky ReLU activations. Residual connections basically add skip connections between different layers of the network so that information can directly flow from one block to the next, reducing gradient vanishing problems common to deep neural nets. The neck then downsamples the features from the backbone to our target grid size, meaning that if the backbone output is a 512 by 512 feature map and our target grid size needs to be 32 by 32, we would apply the downsampling 4 times, reducing the feature dimensions by 2 each time. At each downsampling stage, I also doubled the number of channels in the feature map to prevent the loss of excessive information. It's question time again. What do you think are the main reasons for downsampling? Well, downsampling allows later layers of the network to capture information from a larger portion of the original input image. Intuitively, the feature maps at the earlier layers of the network can only capture low-level patterns like specific edges or corners, while the deeper layers capture more global patterns. This detail will be super useful when we discuss FPNs later in the video. After we have our multi-channel feature maps equal to our target grid size, it is now time for the head to predict the target bounding boxes at each cell. Since we want to predict 3 bounding boxes per cell and each bounding box has those 9 values, we will output a vector of shape 27 for each grid cell. Therefore, the final output of the YOLO network for a single image will be 32 by 32 by 27, which of course we can then reshape to get our 3 by 32 by 32 by 9, the same as our ground truth labels. Next, it is time for us to apply our loss function. The loss function will contain 3 main components: the objectness score, the class loss, and the box loss. The objectness loss is just a binary cross-entropy loss between the target and predicted objectness score. Box prediction is going to be a regression problem where we reduce the mean square error loss between the target and predicted vectors for the center x, center y, width, and height. And finally, the class loss is going to be a softmax loss for the multi-class classification problem to identify which class a detected object belongs to. These 3 components optimize all the predictions across all of the detection layers. Finally, to put it all together, our training loop looks like this. We loop over a set number of epochs, and for each epoch we loop over all the batches from our dataset. We do a forward pass, compute loss, optimize gradients, and then watch our loss go down. After the model predicts the grid cells, we will have to convert it back to the annotation space of the class ID center x, center y, width, height list. And we do this using this Python function. Here we loop through each batch detection map and grid cell in the targets array, extract data for each cell, and apply the sigmoid function to the objectness score. If the objectness score is above the given threshold, say 0.5, we calculate the normalized center coordinates, the width and the height, and finally the class ID is determined using the maximum class score from the predicted vector. We also record the model's confidence score for each bounding box by simply finding the product of the objectness score and the maximum class probability after softmax. And bam, we are now predicting bounding boxes and classes for objects in our images. After that's done, it turns out the model is doing pretty decently. There are still some issues here and there, mainly some smaller elements don't get detected correctly. For example, the ball sometimes does not get detected at all. So why do you think our network is struggling to identify small objects? I think the main reason is that because we are downsampling the image so much from the 512 by 512 to this 32 by 32 grid, we are losing a lot of information, and those small objects like that ball is getting too smoothed out and not provide any relevant features for the final predictions. And we can kind of solve this using multiple different approaches. In fact, there have been so many major innovations made on the basic YOLO-Darknet architecture that we just discussed, like introducing specialized anchor points, CSP networks, dynamic label assignments. We won't be discussing all of them here, but we will implement one feature that should address our ball problem. But we will implement one feature that should drastically alleviate the problem of detecting small elements. In the next section, let's learn about feature pyramid networks to improve this even further. So the feature pyramid network, or FPN, improves YOLO's ability to detect objects of varying sizes within the same image. It does this by merging feature maps from different layers of the network, which each capture different levels of detail. Let's see how it does this. Basically, as the image passes through the backbone, it gets downsampled. Then the neck upsamples the image back, and while upsampling, we also get lateral connections between the same layers from the backbone itself. In the literature, these downsampled images are also called the bottom-up pathway, and these upsampling layers are called the top-down pathway. You might wonder, what exactly do these lateral connections even achieve? Well, remember that the shallow layers of the network can only capture very low-level but high-resolution features. It's high resolution because the size of the feature map is quite high, but it is low-level features because the shallow networks can only access a very small part of the original image, so it can only detect specific edges and specific corners from the input image. In contrast, when the network passes through several layers, it gains more semantic understanding because it's able to capture very highly nonlinear and global level patterns from the image. So basically, these lateral connections are combining low-level features with high-level features, and it's doing it at multiple different resolutions. Finally, let's talk about the head network. In the previous network, we had just a single head network, but in feature pyramid networks, we have separate head networks at each resolution. The final YOLO loss is just going to be the average of the losses of each of the three heads. Then this basically means we try to predict bounding boxes at multiple different scales rather than just one. And hopefully by doing this, because we are also capturing high resolution features, small objects like the football will now be detected by our network. That sort of explains what feature pyramid networks does. The backbone consists of a bottom-up pathway. The neck consists of a top-down pathway with upsampling and lateral connections. Then we have a multiple prediction heads and multi-scale outputs at different resolutions. Let's go train this and see our loss go down again. Display the annotations on the input images, and it appears that we suddenly have a lot of bounding boxes. So why do you think there are so many bounding boxes now? Pause and try to think for yourself. Well, since each head of the network is detecting the same objects, we are basically getting a lot of duplicate bounding boxes that are essentially the same thing, which are overlapping and pointing to the same objects, just at different resolutions. To solve this, we need to apply something called as the non-maximum suppression, or NMS, to filter out redundant bounding boxes and retain only the most confident ones for each detected object. NMS works by using the intersection over union, or IOU score, to measure the overlap between any two pair of overlapping bounding boxes. Basically, first NMS is going to sort all the predicted bounding boxes based on the model's confidence scores. And again, the confidence score is just the product of the objectness score and the class probability. Starting with the highest confidence box, NMS loops through all other boxes, and for each comparison it calculates the IOU, a ratio that measures how much the boxes overlap relative to their combined area. If the IOU between the boxes exceed a predefined threshold, like say 0.4 or 0.6, the box with the lower confidence score is suppressed or pruned away from the final list of bounding boxes. This process is repeated in a loop, and in the end we have a new list of annotations that have pruned away the highly overlapping low confidence bounding boxes from the model's prediction. And all we need to do now is to extract each frame of our video file, run them through our YOLO network, and watch as it detects players and football for each frame. It is not super perfect, but it does get the job done, and I'm quite happy with these results, especially considering the fact that it's entirely trained from scratch with only 300 images. I'm pretty sure we can make this model much better by pre-training on a larger object detection dataset like ImageNet or Coco, but I leave that exercise up to you guys. Again, I'm going to be uploading all of the code on my Patreon, so if you're interested, please do check out our Patreon link. Because of the multi-scale object detection, we rarely miss objects anymore, even smaller ones. There are still times when the football doesn't get detected because it got lost in the crowd and the model can't capture it, but we will discuss some nice solutions for this problem in the next video. In the next video, we will also discuss how to classify which player plays for which team, and then map everyone into a 2D football field where we can track individuals as they move. So please make sure to subscribe to the channel and hit that notification bell icon so you get to watch it as soon as that next video comes out. As usual, you have been magnificent. I hope you learned something from this video. I will see you next time.